Hello there. I'm going to begin a completely new module with this lecture. What we are going to do are a bag of techniques called symbolic testing techniques, which I said I would do at the end of this course. So symbolic testing broadly includes a new set of testing techniques which are actually speaking more than a decade, more than 3 decades old, but have become popular now. So over the next 4-5 lectures, we'll exhaustively understand symbolic testing. So before I move on with symbolic testing, if you remember right in the first week, I told you about things that we will not do as a part of the testing course. And one of the things that I said we will not do is related to proving programs correct, which broadly use a bag of techniques collectively known as formal methods. Program proving means taking a program and showing that it works correctly no matter what. What do we mean by no matter what? That is, if given any input that is legally acceptable by a program, it will always produce correct output. Now, one thing to be noted before we move on is that program proving is different from program testing. When I test a program, all that I do is to give some inputs using carefully designed test selection methods, which we saw almost throughout the course, and check if the program works on these test inputs correctly. Now we all know that exhaustively you can't go on giving test inputs to a program. It's not feasible and it's not necessary also. That's not the goal for testing. It's to be able to cleverly design test case techniques that will find the error. Given that we can't exhaustively test a program, what we can do using testing is to show that on the inputs that we have tested, the program does the way it is supposed to be doing. It either works correctly or it has an error. We cannot make any claim about the inputs that we have not tested the program on. Hence, program can never be proved to be correct on the other inputs. Program proving deals with proving a program to be correct, and that involves a bag of techniques, as I told you, which are called formal methods. What are formal methods? I'm not going to introduce you even to a cursory extent of what formal methods is. I'm just listing here so that if you're interested, you could look up for other courses on NPTEL or other material in this area. Formal methods, as the word formal says, involves mathematical techniques that are based on taking a particular software artifact, code, design, requirements. You derive formal models from that and then you verify or validate a program. Formal methods, because they're formal, have mathematically sound semantics. There are 3 broad categories of formal methods available: model checking, theorem proving, and program analysis. There is a currently running NPTEL course on model checking. Now, program testing, as I told you, is what we've dealt with in the course, testing a program. And at the other extreme is program proving, which is proving a program correct. They can be thought of as extreme alternatives. One doesn't replace the other. They both can be used together, and if you've proved a program correct, it doesn't mean that you need not test a program. If you've tested a program, it does not mean that you need not prove a program to be correct. They're complementary. In fact, they're considered as extreme alternatives. In testing, as I told you, you can be assured that the sample test runs work correctly by checking the results. The actual output, does it match the expected output or not? And correct execution of program on inputs that have not been tested is still in doubt. No sweeping claims about saying the program is correct because it's working on all my test inputs. That's wrong to say. But program proving, you don't actually execute it one vector at a time, one test vector at a time. You use a bag of techniques that I've listed here to mathematically prove that a program meets its specification. What is the specification? Is any requirement about a property of a program. It could be a requirement that says that the program meets its functionality of a certain kind, and so on. It may or may not involve executing the program. And the thing to be noted is that unlike testing, where there's heavy automation, program proving cannot be automated at all. Typically, model checking is where there is automation possible, but it's not scalable for all kinds of software. In theorem proving and in program analysis, full automation is never possible. Proofs are done by hand. What we are going to do is symbolic execution, as I told you. Symbolic execution can be thought of or has been introduced by several papers that deal with this as a practical approach that sort of stands in between program testing and program proving. Symbolic execution is basically a testing technique. That's why we're looking at it in this course. It again executes a program, but it doesn't execute the program the way we have seen it till now. It executes a program in a particular style called symbolic execution. That's the term. So we'll understand what that term is today. Each symbolic execution can be thought of as executing a program on a large set of actual inputs. So I'll explain it through an example. Here is a small piece of code, very small piece of code. What does it do? It takes three numbers, A, B, and C. Don't worry about what their types are. It's not given here. It's not important for us. Let's assume without loss of generality that they are integers. Takes these three numbers A, B, and C, and then what does it do? It computes the sum of A, B, and C, but it does it in this roundabout way. It first adds A and B, stores it in X. Then it adds B and C, stores it in Y. Please remember, it's supposed to add A with B and then with C. But by then what it does is that because it's adding B twice between X and Y, when it finally computes Z by doing X plus Y, it subtracts 1B. It's just some way of writing the program. May not be the most intuitive way, but for some reason, let's say it takes it like this. And then it returns Z, which is the sum of A, B, and C. Let's say I give you the task of testing this program. What will you do? You will give some values to A, B, and C based on some criteria, and then test the program. You will see what for these values of A, B, and C that you have given, what is the expected output. Then you will run this piece of program and record the actual output and see if the expected output matches the actual output. If it does, then you say that the test case is passed. So our actual test statement will look like this. So let's say the inputs that you're going to give to the program A, B, and C are 1, 2, and 3. I have written it here. A is 1, B is 2, C is 3. I'll come back and tell you what these question marks are. What these question marks mean is that as you give inputs A, B, and C as 1, 2, 3, let's say you're maintaining this table which records what happens after these 5 statements in the program are executed. What are the 5 statements in the program? You go back to the program, these are the 5 statements. The first statement is just the function name, second statement is this, third statement is this, fourth statement is this, fifth is the return statement, sixth is the end statement. So you keep this table where you give inputs A, B, and C as some concrete values. In this case, let's say 1, 2, and 3. And then in the statement, you record the values of the variables in the program as the program executes. There are 3 other variables in the program, X, Y, and Z. X and Y can be thought of as internal variables. Z is the variable that is returned. So after statement 1, which is the first statement in the program, which lets you pass inputs as A, B, and C, X, Y, and Z are not assigned any values. That's why there are these 3 question marks. After statement number 2 executes, X becomes A plus B. What is A? 1. What is B? 3. So A plus B is 4. So X becomes 4. I've put these dashes to say that they can be interpreted as values have not changed, in the sense that I still don't know what Y is, I still don't know what Z is. A remains 1, B remains 3, C remains 5. If this is confusing, you copy exactly what was there in the previous row here. That's what we mean by this dash. Now after statement number 2, which computes Y as B plus C, Y gets assigned value 8. All other values remain the same. Similarly, after statement number 3, what does Z do? Z is X plus Y minus B. That will be 4 plus 8, which is 12, minus B is minus 3, 12 minus 3 is 9. What does line number 5 do? Line number 5 returns 9. Using this statement, you see actual output is the same as expected output. Yes, then you say my test case is passed, otherwise you say my test case is failed. Now let's say you decide to give another set of inputs to the program. Instead of 1, 3 and 5, maybe you will give 0, 0 and 0. To see what happens, how the program behaves. For the same set of inputs, you will again do the same thing. You will give the inputs, look at the expected output, look at the actual output, compare and see if the test case is passed or failed. You can repeat the process for another set of inputs, repeat the process for another set of inputs, and do on carry on till your test criteria is met, or till you are satisfied as a tester that the program is working correctly, or when you reach a state where you know that the program is erroneous. In this case, the program segment that is given here is not erroneous, so it does work correctly. Now let's assume that instead of giving these concrete values as 1, 3 and 5 or any other concrete values, let's say I want to execute it symbolically. What I will do in that case is that I will say A is not 1 or any concrete value. A is some symbolic value, let's say alpha 1. B is another symbolic value, let's say alpha 2. C is another symbolic value, let's say alpha 3. I'll come back and tell you what this last column is. The rest of the table exactly is a replica of this table, but instead of having concrete values here, it executes it on symbolic values. How do you interpret symbolic values at this stage? Think of symbolic values as being placeholders for concrete values. So when I say A is alpha 1, you can think of A as being taken the symbolic value alpha 1, where alpha 1 will eventually be one concrete value. Similarly, B is also symbolically alpha 2. Alpha 2 could represent any abstract value for B that matches the type of V, eventually be substituted by a concrete value for B. Similarly for C. The rest of the table is the same. It says in statement 1, X, Y and Z are not yet assigned. After statement 2, X becomes alpha 1 plus alpha 2. Y and Z remain the same. All these remain the same. X remains the same here. After statement 3, Y becomes alpha 2 plus alpha 3. Z is not yet assigned. Alpha 1, alpha 2, alpha 3 are the same. After statement 4, X and Y are the same as before. Z becomes this and so on. Is this clear? And what is the program return? This table is the same as this table. There are two differences. One is here A, B and C are given concrete values as input. A, B and C are given abstract or symbolic values as input. Everything else is the same. The last column represents what is called a path constraint or a path condition. PC is short form for path constraint. Path constraint here is marked as 2. You can think of it as, you remember our reachability, infection and propagation condition? You can think of PC as a set of conditions that collect those predicates, corresponding to reachability, infection and propagation. If you see this program, it doesn't have any decision statements, any branching statements. So reachability is always true. Infection and propagation will also be eventually true. There is nothing like a path constraint here. So the path constraint is marked as true, right? So this is how a program is symbolically executed. So just to repeat what I said, you want to symbolically test or execute a program. The program looks like any other normal program written in, let's say, C or Java or whatever programming language. For normal testing, you would give concrete values to inputs. Like in this case, you would give A1, B3, C5. In symbolic testing, you would give symbolic values to inputs. And then what do? You collect expressions corresponding to internal variables. Because you have not given concrete values, you can't evaluate an expression X is equal to A plus B. You can only collect another expression in terms of the symbolic variables. One natural doubt that might come to your mind or that you might ask yourself is, what am I doing differently than what is given in this program here? Instead of writing A plus B, I am writing alpha 1 plus alpha 2. Instead of writing B plus C, I am writing alpha 2 plus alpha 3 and so on. That's natural. In some sense, we are not doing anything. We're just saying that alpha is an arbitrary placeholder value for A. Beta is another arbitrary placeholder value for B. Alpha 2 is another arbitrary placeholder value for B, and alpha 3 is an arbitrary placeholder value for C. That's exactly what is symbolic execution. I'll illustrate it with another example. This time it's a slightly bigger code. So let's go through the code first. So here is a program. So it has a function called twice, which takes an argument of type integer given as variable v, and it returns an integer type. It's just a one-line function. What does it do? It multiplies v by 2 and returns it. Nothing else. Now there is another program which is called test me. These names are given just for improving readability. There's nothing else to it. This program test me returns what? It takes two arguments x and y. So what does it do? The first line, it calls this function twice. It might as well directly said z is equal to 2 into y, but I have just set this to illustrate a particular point that I will come back to. So it calls the function twice, which basically multiplies its argument by 2, assigns it to z, and then what does it do? It says if z is equal to the other input x, then you go and check for one more condition. If x is greater than y plus 10, then you say the program reaches an error statement, reaches an error state or an error condition. I have not explicitly written what the error condition is, but indicated more like that there is an error just by writing it as error. It may not syntactically be legal in any programming language, but think of this as representing an abstract piece of code that indicates an error. Or you can think of it as printing an error state. So what does this program do? This program is very simple. It takes two arguments x and y, does z is equal to twice of y, then passes two if conditions. First checks if z is equal to x, then checks if x is greater than y plus 10. Both the if conditions are passed, it says there's an error, otherwise it doesn't do anything. This is the program. Then this is being called by main. Main calls test me, and then it says return 0. And I have also said what are inputs x and y to test me. I say x is given as a symbolic input. Read this sym underscore input as x is not being given as a symbolic input. Similarly, y is being given as a symbolic input. Now, before we move on and understand how symbolic execution works for this program, what do I hope to achieve? I'm telling you that there is an error in the program. Using symbolic testing, my goal would be to find this error. When can I reach this error? I can reach this error if this if condition passes and if this if condition passes. You might want to spend a minute thinking about which will be the values of x and y for which both the if conditions will pass. This is a small enough program. If I look at this program for a couple of minutes and study its code, I will be able to come up with two values for x and y such that both the if conditions pass and I will reach the error statement for sure. Let's say instead of staring at this program and thinking about it manually yourself, you want to be able to systematically do it. How will you do it? Let's say here is a way. So I'll draw what is called an execution tree of a program. What does this execution tree of a program tell you? This can again be related to our reachability, infection and propagation condition. Right in the very first statement, after calling this function twice of y, I can always reach here. There are no if conditions. This is the first place where a decision takes place. If this if condition itself is false, then this program exits. Suppose this if condition is true, then it goes into the second if condition. That's what this node captures here. So it says this is the first if statement that is encountered. It can be true or it can be false. If it is false, then the program does something. If it is true, then the second if statement is tested, which in turn can be true and false. Now, what are these three leaf nodes in the tree that I have given you? I have given you an example test case that will make this if condition false. For example, if x is 0 and y is 1, then this if condition will be false. Why? Because it says 2 is equal to 0, which is false. So this can be thought of as a test case that will make this false. If this is true, which is some test case, it could be either this or this, I will go ahead and test the next statement. So a test case, for example, x is equal to 2, y is equal to 1 will make this one true and then this one false. Similarly, a test case, for example, x is equal to 30 and y is equal to 15 will make both the if statement true, and this is the test case that corresponds to the error. So ideally, to exhaustively test this program or to do edge coverage or branch coverage or predicate coverage for this program, you make this statement true once, false once. You make this statement true once, false once. That's what this does. This test case will make this statement false, the first if. Then any of these test cases will make this if statement true. And this exclusively will make the second if statement false. This will make the second if statement true, which will hit the error. So symbolic execution, what it does is, it will go back to this program. It will try to not give concrete values for x and y. It will give symbolic values for x and y. And what it will do, it will collect constraints corresponding to these if conditions. Towards the end, it will try to solve the constraint and try to automatically obtain these values. That's what symbolic execution does. So symbolic execution uses symbolic values instead of concrete values as inputs. Inputs means test case inputs. Program variables are represented as symbolic expressions over the symbolic input values. Like, for example, here, going back to the previous sum code, there were 3 program variables, x, y, and z. When I symbolically executed them, I represented them using symbolic expressions. I represented x as alpha 1 plus alpha 2, y as alpha 2 plus alpha 3, and so on. Right? So that's what is written here. Program variables, which are internal variables in a program that don't correspond to inputs, now become symbolic expressions as the program runs. A symbolic expression can be thought of as just an arithmetic expression that is there already in the program, but has symbolic variables because it's not being evaluated. Output values also are a function of symbolic input variables. What is a symbolic state? Symbolic state at any point in time gives me the symbolic values of all the variables. Like, for example, here, going back to the sum program, if I read this at any point in time, I get a symbolic state. It says x is alpha 1 plus alpha 2, y is alpha 2 plus alpha 3, z is not yet assigned value, a is alpha 1, b is alpha 2, c is alpha 3. The program is executing statement number 3. That's what a symbolic state will say. Symbolic path constraint, it is what we've introduced logic, if you remember, as per the logic that we introduced. It is a quantifier-free predicate logic formula, or it's a quantifier-free first-order logic formula. Predicate logic is the same as first-order logic. Obviously, there are no quantifiers, and the path constraint is a normal predicate logic formula. If you go back here, the path constraint to reach this statement will be this is true and this is true. The path constraint to reach this statement would be not of this, because that's when this becomes false. For an example program like this, there are no path constraints, or path constraint is just the Boolean constant true, because there are no decision statements in this program. So I'll just quickly repeat what I said in this slide. Symbolic execution symbolically executes a program over inputs. All the internal variables of a program, every internal variable will have some expression in the program that evaluates it. Instead of evaluating it, you just substitute it with symbolic variables and keep it as symbolic expressions. A symbolic state will be a large tuple that gives symbolic values or symbolic expressions for the inputs and the variables in the program. Along with that, I collect path constraints, which can be thought of as all the decision statements that you encounter in the program. Take the statement as it is when it is true, take the negation of the statement when it is false, keep ANDing them. And since there are no quantifiers here, it's a quantifier-free first-order logic or a predicate logic formula. What does symbolic execution do? In software testing, symbolic execution is used to generate a test input for each execution path of a program. As I told you, if you go back to this tree, an execution path is a sequence of true, false values, right? If I take this is a path of length 1, which makes the first condition false. This is a path of length 2, which makes the first condition true, second condition false, and so on. So a path constraint or an execution path is a sequence of true and false values, where true at the ith position in the sequence denotes that the ith conditional statement is true, or it took the then branch, and a false in the ith position denotes that the ith conditional statement took the else branch. This should be obvious as we see it in that example, and we represent the execution paths using an execution tree. This is an execution tree. So at the beginning of symbolic execution, the symbolic state sigma is assigned an empty map, which is dash 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 or question mark question mark question mark. At every read statement, it assigns a symbolic variable. At every assignment statement, it assigns a symbolic expression, like here, for example. There was this statement which can be thought of as a read statement. After statement 1, symbolic values are assigned. After statement 2, symbolic expression is assigned. That's what I mean. At every read statement, symbolic execution adds the mapping assigning variable being read to its symbolic variable. At every assignment statement, it adds a symbolic expression. Now path constraint. Path constraint initially is true to start with. The moment you get a first if statement, if E then S else 1, S1 else S2, this is how it looks like. E is actually the condition. Whatever your path constraint was, you AND it with sigma of E, which means take E, substitute it with symbolic expression and AND it. This is for the then branch when that condition evaluates to true, and you have to AND it with negation of sigma of E to represent the else branch for the condition to be false. Like for example, if I go back here, there were two path constraints, one for this if and one for this if. Till I come here, path constraint is true, and then I'll do true and z is equal to x for 1, and I'll do true and not of z is equal to x. So true and z is equal to x will make this take the true branch. True and not of z is equal to x will make this statement take the false branch. And when I come here, I already had 2 and z is equal to x. If I negate it with and of, if I AND it with x greater than y plus 10, then I get this. If I AND it with not of x greater than y plus 10, then I get this. So that's what it said here. As you're running a program, executing a program, you would have a path constraint. For every if statement that you encounter, you AND it with E once and you end it with negation of E once. ANDing it with E intuitively represents the program taking the then branch. ANDing it with negation of E represents the program taking an else branch. Finally, what you do, you would have collected a path constraint, like here, you would have collected this constraint and this constraint. You solve it. Means you give it to a solver. Solver will return values. Say for this to be true and this to be true, here is one value. If x is 30, y is 15, both are true. This becomes your test case that you execute the program on. And similarly to how do you get this test value? You solve this and negation of this. Then this will be the test case. How do you get this test case? You solve negation of this. So each path constraint is solved, and if there is a assignment, then the program will continue along the then or the else branch, right? If a particular path constraint is not satisfiable, for some reason it cannot be solved, then you say symbolic execution terminates then and there. So at the end of symbolic execution, path constraint is solved using a constraint solver. There could be third-party constraint solvers. If you remember, when I introduced propositional logic to you, I told you that the satisfiability problem for propositional logic is an NP-complete problem. It's a hard problem. And the satisfiability problem for predicate logic in general is undecidable. But there are lots of constraint solvers. DReal is one of them that I use, that you can use to solve these path constraints. And if concrete test values come, then they become your concrete test inputs. What do these concrete test inputs achieve for you? Let's say the concrete test inputs will achieve by how many path constraints you have here? 3 different path constraints. 2 path constraints, but their combinations give you 3 conditions. By giving it and solving, what you're guaranteed is you're guaranteed exhaustive coverage of a program. With just 3 test cases, you can completely cover this program. Test this program for every behavior that is possible in the program. That's what is written here. So it says that if a program is executed on the concrete input values that the constraint solver gives you, it will take exactly the same path as the symbolic execution and terminate the same way. These concrete inputs ensure that coverage is achieved in testing. You will be able to take different test paths in the program. We'll see a few more examples where this is illustrated very clearly. Like for example, this is the example that we saw, the same code I'm showing you here again. I'll just walk you through the steps of symbolic execution. After executing these statements 12 and 3, the symbolic inputs x0 and y0 are assigned to x and y. And after executing line 5, which is this line, x0 stays as x0, y0 stays as y0, z becomes 2y0. This is a symbolic expression. And after line 6, where you encounter first if statement, one which passes x0 as 2y0, the other one is failing x0 as equal to 2y0. Now, when it passes, you go to the inner if statement where you take this condition x naught equal to 2y naught and AND it with the condition of the second if statement. And you take the same condition x naught is equal to 2y naught and AND it with the negation of the if statement, which amounts to x naught less than or equal to y naught plus 10. So you have three constraints that you have collected. First one is x naught not equal to 2y naught. Second one is x naught equal to 2y naught and x naught greater than y naught plus 10. And third one is this. Let's say you give these three constraints to a constraint solver, then you can get some values like this. These are just one set of sample values. Any values that solve these equations, satisfy these equations are good enough. This is a small example, so you could just look at it and do this yourself. So the value of symbolic execution may not be seen, but let's say you're running it on a large enough example, then actually collecting these constraints and solving them will help you to drive program execution to a particular path. So symbolic execution is valuable from that point of view. So I'll stop here. In the next lecture, I'll continue with symbolic execution. We'll look at additional examples of code that involves loops and so on. Thank you.